Okay, can you guys hear me now? Great, cool. So, hey everyone, I am Greg from ENS, and we have Tate here as well. Today we're going to be talking about interoperability in ENS v2. But before we talk about v2, is this working? Nice. Before we talk about v2, I want to take a step back and talk about what is ENS in case some of you guys don't already know this. So the Ethereum name service is a decentralized, permissionless naming protocol that lives on Ethereum mainnet, very specifically. And the most basic level is that we turn complex hex addresses into human-readable names, right? So instead of typing OX179A, so on, into a wallet, I can type gregskril.eth, and that is my on-chain identity. That is a pointer to my wallet. And this just sounds like a username, a name to an address. But really, over time, it's become more of a profile. And so this is a look of my ENS profile. I do have the address, as you can see, but I also have a description that I like baking and building apps on Web3 protocols, and an avatar image, and all these other social protocols, and addresses on other chains as well, EVM and not. And so this is kind of what becomes my portable Web3 profile. Another look at how you might see this in an app. On one hand, you connect to an app and it shows you your address. This doesn't mean anything. A Web2 user that's coming into crypto sees just a random string of numbers and letters, and this is meaningless. It's not personable at all. Whereas with ENS, you have a more personable connection into your app. You sign in, and you have a name, you have an avatar. This feels like my account, my portable Web3 profile. And not to be like shilly, but ENS has been around for a while. There are over 1 million active .eth names and hundreds of integrations. All of this is to say that it's worked pretty well so far. But in order to scale to what we want it to be, and for the average user to be able to use ENS and register a .eth name without kind of understanding all of crypto, we need to improve. And so if you have registered a .eth name in the past, you may have seen a screen like this. And there's a lot going on, so let's kind of point out a few things. First is that there are 3 steps, and these 3 steps take at least a minute to complete, which is kind of slow. Users aren't used to waiting a minute just to do something in an app these days. Next, you'll notice that when I took the screenshot this morning, gas fees were over 10% of the actual fee of the name. And when you think of it in percentages, this is just kind of crazy for normal users. Web2 users are not used to this. We kind of talk badly about credit card transaction fees, and those are significantly less. And again, this is on a good day. There are times where the transaction fee is multiples of the actual fee. And speaking of the fee, it always has to be paid with ETH on Ethereum mainnet, on L1, which it is increasingly unsafe to assume that the average user has ETH on L1. And so these are kind of some of the problems that we see and that we seek to solve in the next version of ENS. But just a funny way to think about this is that ENS sees itself as a user experience protocol. It tries to make crypto easier to use for users, but actually, our own user experience isn't the best. And so, like the experience of registering a name. And so this whole upgrade of ENS v2 is trying to improve the UX of ENS so that we can better serve the whole ecosystem as a user experience protocol. Yeah. And so what does making registration easier look like? It looks like some of these things. A user should be able to register a name quickly, starting on any chain, starting with any token, in less than 2 wallet interactions, which we have today. So obviously, we don't want to make it worse. They should be able to use any wallet. They should be able to use any client, meaning any website should be able to implement this stack that we're about to talk about. It should be completely permissionless and as trustless as possible. So these are kind of the requirements that we have in building out ENS v2 on Namechain. And this basically makes it obvious that ENS needs some sort of account abstraction. You need account abstraction, you need chain abstraction, all these things. But actually, when you look at the current stack of account abstraction, it becomes clear that the exact pieces don't solve all of our problems together. And so we have to come up with a little bit of an innovation on top of the existing stack. And so that's what I'm going to bring Tate on to talk about.
Hey guys. About account abstraction on Namechain, the current account abstraction options are essentially between two sectors. We've got wallet-based and app-based account abstraction. On the wallet side, we've got 7702 or a straight SCA implementation with like a passkey signer or something. And on the app side, that tends to be just standard SCAs. So with wallet-based account abstraction, our issue generally is that it requires a specific wallet. 7702 is a great specification. However, many wallets, unfortunately, do not implement 7702, and as such, we can't give the benefits of 7702 to every single user, like all of the account abstraction stack. And that's a significant problem for ENS because we want to reach as wide an audience as we possibly can. We want to be globally inclusive, and even if the biggest wallets support us, support 7702, that is not 100%. It's never going to be 100% in terms of getting an ideal flow, but we'd much rather be on the higher end of maybe 90% or more. Yep. So app-based account abstraction is the other main option, but it's only the app that can touch the assets if you're using this method. The issue with that is that we don't have any freedom for the user built in to do whatever they want to do. Migrate to a different wallet, use the functionality of names through a different system, etc. Or if you don't want to have the app solely authorized for anything, then you need explicit authorization from the user, which is an additional wallet interaction. And as Greg was mentioning before, one of our requirements is that we want to keep it to 2 wallet interactions or less for registration. And for any other interaction on ENS. Then the alternative to both of those things is having some sort of lookup system that every application can implement. So to outline a specification of what we really want is account abstraction, but you can use any wallet. You can access it with any supported app, or if you have an unsupported app, it should still work via a user's wallet, and on both Ethereum and mainnet and Namechain. That is another crucial step in that we can't have a chain native solution because ENS v2 spans multiple chains, not just a single chain, and we don't have, well, we have a say, but we don't have any control over what happens on Ethereum mainnet. So what we're creating are hidden contract accounts, or HCAs as we're calling them, and essentially it is just a dedicated SCA or a smart contract account implementation, but with a lookup mechanism built in. The lookup is really just a mapping, and that mapping is really dead simple. This is nothing insane. This is not some crazy new architectural decision that we've decided to make. It's a simple mapping, and it enables the benefits that we want to get for SCAs for every user, like basic multi-call gas sponsorship, and everything that's beyond that hasn't been discovered with modular accounts, as well as what I'll go into detail in a sec about in-browser burner signers, which is allowing us to keep our wallet interaction limit very low, and in some cases even be able to achieve a full registration process in a single wallet interaction, which is really nice. So The lookup is just on an HCA factory contract, and it's just one HCA factory contract, and it recognizes a single implementation, and it can maintain a mapping of a HCA address to an account so that you can do a reverse lookup whenever you need authentication for anything. For example, if you are checking for ownership authorization, then you can use your HCA and the ownership authorization checking message sender will then use this lookup using the HCA address and resolve it to the main account, where it will then be authorized to do exactly the same thing that the main account would be able to do without any extra steps beyond that, and is very simple to implement. So on the implementation, we've chosen to go with OpenZeppelin's pre-existing context pattern, which establishes a message sender function that you should call instead of message.sender whenever you're using a Solidity function. And we're just replacing it with HCA context, which I'll show you in a second. And it's a very simple implementation, but for a developer who wants to utilize HCAs, this is literally all that you need to do from a contract side to be able to recognize HCAs. And then once you're part of that ecosystem, you get all of the same benefits that all of our protocol contracts are going to get as well. So that's not something that I included here, but all of our protocol contracts will recognize HCAs just as they would recognize accounts. And so you just need to initialize it with HCA equivalents, which again, I'll show you in a second. So let's look at some code. Let me just enlarge this a little bit. So we've got the HCA equivalence function, and it's the message sender underlying implementation. All it's doing here is we're just checking for a factory address, and then we're going to do a lookup on the factory for an account owner from the HCA address, if it is an HCA address, assuming that there's no insane hash overlap, that will just return 0 if there is no main account, aka if it is an HCA, if it is not an HCA. And so we're just going to return the message sender. Otherwise, we're going to return the account owner instead of the HCA. And so then all of your ownership checks, all of your permission checks, if you're familiar with ENS, name wrapper fuses would theoretically use this lookup instead of any custom authorization logic on top. And we're implementing it in HCA context itself, just like this. So all we're doing is we're just replacing, so this is the OpenZeppelin context contract, and it just defines a message sender function, and we're just replacing it with a call to our HCA equivalents, and that's all it is. It's dead simple, but that's the implementation. As for the code itself, the SCA itself, we've got someone from Rhinestone here who can take you through a video of a demo, I believe. Let's quickly put that up. Take it from there. Yep.
We're good. Can you guys hear me now? Nice. Well, thanks for coming, guys. I'm Conrad. I'm from Rhinestone. Been working with the guys at ENS. So yeah, essentially kind of continuing on from what Tate was talking about with the HCAs. I wanted to show a quick demo in terms of what the whole experience looks like. Obviously, this is just kind of like a demo app and not kind of like final UI. But I guess I'll walk you guys through the whole experience of kind of using the HCAs, but also kind of seamlessly going cross-chain. So starting on Sepolia and going to base Sepolia. In the future, that will obviously be kind of the ENS Namechain. But yeah, I guess let me get started with the demo. So obviously here we just have some demo UI. Is this full screen? No. Does that work? Shit. Okay, never mind.
So hard to
Okay, never
talk
mind.
with the.
Anyways, so this is the demo. You kind of connect the wallet. You can just connect any EOA that the user has. And I guess the important part here for the demo is yeah, just showing that we have some USDC on Sepolia. And then pausing here quickly, it spins up an HCA, as you can see here on base Sepolia, which in the future will be on Namechain. And the idea is that this HCA, I think I'll show that in a second on the Explorer, it doesn't have any funds, it's not really deployed yet. It's kind of just like the user comes with the EOA, it doesn't have anything else. And so like no balance on base Sepolia in this case and Namechain in the future. And then the idea is that the user wants to be able to go from their existing funds, whether that's USDC, ETH, or any other token, to Namechain and buy the domain that they want, both atomically and quickly, and also without needing to worry about bridging. The idea as well is that it doesn't kind of have to be Sepolia or mainnet, it can be kind of any other chain that the user can move from to Namechain. So entering some domain here, which is available. And as you can see here, the user doesn't have any USDC balance on base Sepolia, but it has balance on like normal Sepolia. So under the hood, when the user does the ENS like registration process, which is what was mentioned earlier, it will also atomically bridge and kind of do that in one go. So that's the commit process. And as you can see here, the user just has to sign a message, which is actually a permit to message. So anyone that has used like DeFi before, like Uniswap, for example, you will have like dealt with permit to before, and that allows you to spend your tokens kind of just with a signature instead of needing to actually make a transaction. And actually going back a second, you can also see here, like here in the bottom left, that the payment token is USDC. So the user doesn't need to have like ETH necessarily, and like I said before, and I think as Greg mentioned earlier, that could be any token in the future. Like the user can literally just rock up with the latest shitcoin and pay both for the fee for the ENS and for the ENS domain and for gas kind of with that token. So going back, the user will just sign the permit to message, and then the transaction will first happen on Sepolia and then kind of on base Sepolia. In this case, because Sepolia is pretty slow, like the block times are like 12 seconds on average, it takes a second, but depending on the chain you're coming from, this will be faster, and also when it's on mainnets, it'll be quite a bit faster. And as you can see here, so far, there's just been a single interaction that the user has signed. So when this transaction has gone through on the destination chain, you can see that the commit, which is the first part of the ENS domain registration process, has gone through on base Sepolia. And as part of that, obviously the user has paid the fee, as you can see here, in USDC. And once again, kind of as I mentioned earlier, there was no USDC, no gas tokens, nothing that the user had on the target chain. So it's a proper kind of app chain experience where a user can just go from funds they have anywhere and just interact with this new chain that they don't even necessarily know about. And kind of showing the user account again, this is now a deployed HCA that has some tokens as well. So then kind of the second process is the actual kind of reveal or the registration step. And as you can see here, there's no wallet pop-up anymore because this is all handled by the local session signer. That's kind of the signer of the HCA on the target chain. So the user just press register and it pretty much instantly goes through because like the app chain, in this case base Sepolia, is just super quick. And then, yeah, just showing that. You can see here that the ERC721 got minted, which is the user's domain. And that's pretty much it. One thing that is also kind of like very easily possible with this is if the user wants to do multiple domains, they can also do everything in one kind of interaction, kind of bridge enough funds to actually register multiple domains so they don't have to even go through that one-click experience. But yeah, that's kind of like the experience. As you guys saw, like the user didn't have any funds on the destination chain, and it was just a simple one-click experience. Yeah, that abstracts away, that the user even gets a smart account, but also that they're actually interacting with another chain. Obviously, in this demo, this was kind of like shown quite well, but I think, and the people at ENS have been working on great UX there, where actually a user interacts with an app on an app chain, but doesn't even know about that because they never have to think about bridging. They never have to like actually realize that there's another chain involved. They just think these are the tokens I have on whatever chain, and everything is super smooth, instant. I can pay gas in whatever token. So yeah, that's kind of the final experience we're going for, and super excited to see this live in prod.
Excellent. So many
All
good
right.
questions from the audience. Guys, I know
So
you want to be super specific, but
now that we've had that demo, I thought might as well take you through a little bit of the protocol code as well as like at the implementation in the protocol. Uh, this is the Namechain repo. So some of these contracts will just be on Namechain, but a lot of them will be deployed across both Namechain and L1. A little bit confusing, but bear with me. So we've got an ERC 1155 token contract, and this is pretty much a standard 1155 contract, except we've just got an additional owner of function for ENS compatibility. So all I'm going to do is search for the context. So we've got HCA context here, and we're just inheriting HCA context, which is what I was showing before. And that is literally the only thing we have to do besides a... Do we actually have it here? Oh, right, it's on the registry itself. All I have to do is search for equivalence. So this is a contract that's inheriting that 1155 contract, and it's just got an initialization of the HCA equivalence, which is, if I can click through, just our containing our function from before, and it's got a reference to the HCA factory. There's only one HCA factory, and that is the only thing that's required because we're already using the message sender helper here instead of message.sender. So anywhere that we use underscore message sender, it's going to be able to detect and replace an HCA address with a standard address. And yeah, so it's completely that easy. There is nothing else to it, and I'll continue on. I've got a few extra things to say here. So we've got the in-browser burner signers, and that's what's removing those extra wallet interactions. We've got an issue with the in-browser burner signers in that users will just sign things they don't understand occasionally. And if the browser signers have unlimited permission, then that can be potentially very dangerous. At the ENS protocol level, this is sort of equivalent to like a 7702. Not exactly the same, but the potential scope you could have in authorizing an in-browser burner signer is the same as a delegation on 7702. So we're reducing it in scope to reduce danger, as well as that the burners all have expiries so that they don't leak, or if you get compromised or something from a data breach a long time ago, etc., that's nothing to worry about. It's all stored locally though, in browser. It's never going to leave your browser, at least our implementation won't leave your browser. It's up to an app to make sure that that is the case, rather than a wallet in some other cases. So for execution, you can use intents, but you can still utilize 4337. Intents are crucial for user understanding, and you can execute it with unrelated data from the SCA or HCA implementation itself. But as a fallback, 4337, which is extremely widely supported, is still there in the case that you urgently need to execute something, or if you have specific infrastructure that you want to run in a different way outside of the intents framework, you have the ability to do that. As for upgradability, we can only have one current implementation, but users can be on older versions. So we'll have just a standard set of versions from 1 all the way forward, and those versions can all be utilized by a user at the same time, not one user, but many users. So we can't restrict just to one implementation, or we don't want to restrict to just one implementation, because users should have the option, in case of a malicious DAO activity, to maintain their SCA as is on the current implementation. Or if they just don't feel the need to upgrade, they don't need to upgrade. And the DAO is the only authority that can authorize updating the current implementation to newer versions. The reason we have to have one specific version is, again, because of safety. We don't want a user to be able to assign arbitrary full access to the ENS protocol on behalf of their account, because like before, it's similar in scope to 7702. It's pretty much just a delegation, and delegating is dangerous. Most wallets won't let you delegate to, or all wallets essentially won't let you delegate to a generic 7702 implementation. They all have their own, or none at all. And that's for safety. They don't want random contracts, and the user really doesn't want random contracts acting on their behalf all of the time and having unlimited authority. And I was saying before, the user doesn't need to upgrade, but they can upgrade. And when they upgrade, they can only upgrade to the current implementation, not to prior implementations in case of bugs or issues where an upgrade is required. So what is that solving? It's faster registration or anything with Namechain. We can use any chain and token via solvers and relayers of Rhinestone. And we can, in two wallet interactions, register a .eth name with an in-browser signer involved. And it's permissionless. Anyone can execute either via intents or via 4337, which is very widely supported across the industry. It's also not completely trustless, but is trust minimized with an in-browser signer auth. Execution itself is still trusted to the extent that you could have, you could be front-run by your solver or relayer for the registration transaction. This is something that we'll be working on over time to try and prevent, but generally the financial incentives don't align for a solver or relayer to front-run a name unless it is explicitly going to be profitable immediately for them to do so. So some future improvements: atomic cross-chain swaps. This is because Namechain is based, and so if you are an L2 and you are also based, and we're settling at the same layer or even using the same pre-confer, we can guarantee execution of a set of transactions on both chains and guarantee settlement at the same time. Unrestricted burner support is something that we would like to add, but again, the unlimited scope for those burners is very problematic. So we need wallets, or at least some wallets, to be able to support parsing what the consequences are for signing access for the wallet, for the signer itself, the burner signer, and potentially making it entirely trustless. Not currently sure how that's possible, but it's something that we're looking into. And so, yeah, that's about it. If there are any questions or queries, then I think there's time for that now. Oh.
So I get like the HCA stuff as a mapping for when you're doing the registration.
We can't hear you.
Can you hear me?
Yeah.
Yeah, okay. So I get the HCA thing as a mapping within the context of registration. Are there other like ENS like adjacent features or functionality that you think HCAs relate to? Or is it really just kind of like isolated for registration?
So registration is the most crucial component up front, but it is technically, like the HCA stack is applicable to any transaction and every transaction on the ENS v2 protocol. The use case for that is more limited in scope if you are looking to just do like a single transaction, because you still have to authorize an in-browser signer as an authority on the HCA. So if you're a random DApp and you want to set an avatar record, you can't do that without any wallet interaction. You still need that one wallet interaction. So for apps that are deeply embedded in the ENS ecosystem, it definitely makes sense to be implementing HCAs. Like if you're creating subname systems or creating intricate resolver systems, then it makes perfect sense. But for everyday, like non-ENS specific DApps, it's not really very useful.
Okay, so it wouldn't be crazy if I was like, yeah, I could like attach session keys to like a record update that's associated to my HCA or something.
I'm not really sure what you mean.
Like I update my record and then it signs so that I have like a session key and suddenly I have this window to do stuff. Does that make sense?
No.
Okay, I'll ask you off stage.
Okay.
Thanks.
Yeah.
Hello, can you hear me?
Yeah.
Yeah, I think it was Tate with the demo. You mentioned that you spin up an HCA in the browser.
So we spin up the in-browser burner signer, which is authorized on the HCA.
I cannot hear you now. Okay.
Can you hear me now? Yeah, okay. We spin up a in-browser burner signer that's going to be authorized on the HCA via a signature from the user's wallet. So we're not spinning up an HCA in the browser, we're just spinning up a burner signer.
Okay. I don't know if now's the time or potentially after, but could you elaborate on like what that actually means in practice and how it's done?
So it's just like a ECDSA signer in browser, like in a secure storage location.
Okay, so you're literally just generating a private key and signing on the fly.
Literally just a private key.
Okay, perfect. And then I think it's actually to Conrad. In the demo, it's obviously a demo, but I'm curious how to, in the context of the current environment, how that bridging was so quick. Yeah.
Wait, can you hear me?
Yes.
The question was, how does the bridging work?
Yeah, how does the bridging work and how is it so quick? Because my understanding is in practice, at the moment at least, that's the kind of main constraint and the issue with user experience is people having to wait for a long time.
Yeah, so that's traditional bridging. There's kind of a new, I guess, paradigm for bridging called intent bridges, which is kind of like, well, I guess it is the intents that Tate was talking about earlier. So the idea is instead of kind of having these canonical bridges where you either like lock up an asset on the source chain or burn it there, and then it gets minted, and then I guess it gets passed through some messaging bridge and then minted on the other side. You instead have these sophisticated actors called relayers or solvers, and you essentially, it's kind of more complicated than that, but you essentially send funds to them on the origin chain, and then they give you funds on the destination chain instantly. So they already have capital, like inventory, on the destination chain, and they would then give it to you there.
So that exists now, and it really is that quick.
Sorry? Wait.
So that exists now. That exists now.
Yeah.
Okay, perfect. Thank you.
Thank you for this illuminating talk, Tate. I wanted to ask you about the HCA factory that includes the mappings. Is that
Yep.
right? Could you tell us a little bit about how those mappings will work, how that data is maintained and then updated as well?
So it's just a one-time operation. So there will only ever be one HCA for any given account. So on the first instance of needing to use an HCA, it'll be deployed, and that mapping is just trustlessly set in the factory contract itself. It just knows what the contract address for the HCA will be for that user, and then it sets the reverse resolution. So it sets the HCA address in the mapping to be equal to the user's account address, and that is stable throughout the entire lifetime of the user's account, or like as long as the chain exists, that mapping will be the same.
And unique, and no possibility of some kind of collision or duplication?
The potential of collision is about as likely as the potential of a collision for generating any account. So, yeah.
Okay, great. Thank you.
Yeah, no problem. Any other questions? Nope. Great. Thanks, guys.